Hey guys, this is for the seniors who are out today, so you missed the notes over Kirchhoff's laws. This goes hand in hand with the PhET simulation, so if you felt like you got a lot of good information from the PhET, then this will be kind of redundant, but it's also a little bit more structured notes over this topic. So Kirchhoff's laws, kind of in the quick version here, under 5 minutes, there's the two types of circuit we've dealt with so far, series and parallel. And depending on how we wire these circuits will determine the resistance and the current that's flowing from our battery through the circuit. So with a series circuit, the first law here, Kirchhoff's current law, states that the current's going to be the same anywhere in the circuit. You can think of this kind of like a water hose, where if you have water flowing through a part of the hose, in every other part of the water hose it's flowing at the same rate. If that didn't happen, you would have water sometimes spitting out and you would have air pockets, and that's not how hoses work. It's the same with a circuit. The same amount of current is flowing everywhere in it as long as it's one continuous pathway. If you have a branching water system where you have like different things going different places, then it's possible to have different flow rates. But here with one big loop, it has to all be the same. With a parallel, if we add up each of the individual paths, they will all add up to the total current. And so in the same way water has to flow continuously through a system, if we had a certain amount of water entering a pipe, that same water is going out through two different pipes. So the way we sometimes summarize this is by talking about how the sum of the current entering a junction is equivalent to the sum of the current leaving the junction. So sigma I in equals sigma I out. You can't get out more than you put in, and you can't fit in more than is possible to flow out through this circuit. The second law is the voltage law, which states that the sum of the potential differences in a circuit has to add up to zero. What that means is whatever positive voltage is being supplied, or positive potential, remember those are interchangeable terms, is being supplied by my battery is used up as it goes through the circuit across each resistor. So we talk about a voltage drop, and that's occurring over the light bulb. So for example, if we have a 9-volt battery here, and there's a 3-volt drop across each resistor, then that adds up. We have 3 and 3 and 3 is 9. 9 volts were produced, so that would give me a net output of 0. For a parallel circuit, it's a little different. On the PhET simulation, when you hook up the parallel circuit, you see that each bulb is equivalent brightness and all of them are receiving full power. The reason for that is because the voltage across each one is equivalent. And if you think about it, it kind of makes sense. If up here, I'm leaving the battery and I have lots of potential, lots of voltage, at the bottom, we know we're going to use up all of the voltage. And so across each one, I would have full charge, full potential. And so V1, V2, and V3 are all equivalent. The last rule is Kirchhoff and Ohm kind of working together to give us the relationship known as Ohm's law in terms of resistance. With resistors, if I add a whole bunch of resistors, one after another, if we go back to our light bulbs here, the more light bulbs I add, the dimmer my bulbs are going to get. It's harder for those charges to flow through the circuit. And so as a result of that, we can simply say that the total resistance is equal to the sum of all the individual resistors. And with the parallel circuit, as I add additional pathways, it actually makes it easier for the current to flow, easier for the charges to get back to the battery. In the same way, it's easier if you're trying to evacuate a large group of people to have lots of different ways to move or ways to walk. And so if I add in all these different pathways, instead of adding up the resistors, I add up the reciprocal of the resistors. So 1 over the total resistance would be equal to 1 over R1 plus 1 over R2 plus 1 over R3. If you don't like this, if the numbers are sounding weird, think about it with a resistor of 2 ohms. 3 2-ohm resistors would give me 6 ohms of resistance. That's quite a bit. Whereas 3 2-ohm resistors in parallel, if I do a half, and a half, that's 3 halves. And then if I take the reciprocal of that, that would be 2/3 of an ohm. So that's 0.6 repeating. And 0.6, obviously much smaller than 6. So you can see that in parallel, it's easier for the current to flow, and so we're going to get more current through that circuit. Lastly, we went through this kind of summary recap. This basically is just an organizational box, and then we drew this circuit diagram, which shows, if I can scroll down enough, it shows here a 12-volt battery hooked to 3 resistors in series. The resistances are different, and they were asked to find the current of each different spot. This was a homework problem. And then in addition, I showed them this one, which had 3 resistors, 1 unknown resistance, an amperage reading, and then also the voltage. And so if you want to look at those two, they're good examples. And then we stopped at that point. So that's all you would need to do.